Well, good morning to everyone. Welcome to one of the educational initiatives here at the CDR, Center for Disaster Resilience of the Faculty of Geoinformation Science and Earth Observation of the University of Twente. And today we're going to present, let's say, the outcome of a collaboration, of a collaborative work with ITC again, and the CNR IRPI Padova in Italy, and the University of Bologna again in Italy, and specifically in a work that we did together with Giacomo Titti, a PhD student from the University of Bologna, also affiliated with CNR IRPI, and we have worked together on a topic that is of particular relevance here at ITC, which is open sourcing. So open source software that can be used by anyone, and specifically in the context of natural hazard, which is a topic that I hold particularly dear, specifically to try and generate susceptibility models, or in other words, let's say models that predict landslide occurrences over a given landscape. So the aim will be to, let's say, assign a label whether a slope is stable or unstable across a landscape of our interest, and then we will do it specifically with a software that Giacomo has written entirely on his own, and specifically via a plugin for QGIS. The most famous open source GIS software currently available for the geoinformation science community. And in this GitHub repository, essentially what you can do is to, you see the repository is the one of Giacomo that he created. That's the link on top. You can use it. And then you will be able to download every single functionality of this software, and specifically this requirement file, where you will initially visualize all the libraries in Python that will be required by the plugin later on in QGIS. So what do? You need to download the data initially. As you can see, you download the entire GitHub project, and then you will see the zipped file. And in our case, we will go in a moment, open that file, you will see the requirement again, the same one you were seeing before, and this will be again the libraries that will be necessary for us to make the plugin work. Once you know them, what you can easily do is to again go and search for a terminal, the OSGeo terminal. You can launch it, and you will see that we have already made some text for you so that you don't need to know all the syntax. But essentially this line of code that we are now showing, you can copy paste it. If you're following us online, you can simply rewrite it yourself and then launch it. So we pasted it on our prompt, but what happened is that in the terminal everything went quite fast because we have already every library installed. For you it may take a bit longer. So once we do this, we can go on our own QGIS interface and essentially open the plugin toolbar. So as you can see, it's highlighted in there. We open the plugin, and what we will need to do essentially would be to call this plugin. So you can follow us in adding this data information, which we will call the plugin as Z for susceptibility zoning. That's an acronym. And you will need to add the URL of it. So again, it's already made for you. You can simply copy the same text. So stop the video here, rewrite it yourself, and then add it exactly in there. And what will happen is that you will press OK. And one key and crucial information is to flag the requirement that you will see at the top of the screen highlighted right now. So please flag it with us. And then what will happen is that you will add the SZ, the tool, in your list of the plugins, which in our case is already installed for us. And for you, that's the SZ. For you, you will need to essentially install it. In our case, we could only have the reinstall option. So you can flag it, and once you do, you will have it already active in your own QGIS environment. So if we now open the toolbox, you will see that the SZ is available in your window. So you can also filter it and make it appear, and you will see that this is a collection of functions. A collection of functions for susceptibility zoning. And specifically, you will see that some of them will be used in these videos, some others will be not. So precisely for those that we will not use in this specific example are these one that I just highlighted, and the reason is we need them for some specific modeling. So for example, for weight of evidence. So a binary model, a bivariate model, and instead today we will focus on logistic regression, so a multivariate statistical tool that does not require all this pre-processing done. So now, in order for us to showcase the toolbox or the plugin, sorry, that Giacomo has created, we will use an example from India, the northeastern part of India. You will see highlighted in a second the region where we picked our data from. And essentially there, what we did was to download the landslide inventory and generate some slope unit or half basin partitions, which you will see highlighted also in a moment, and then calculate for those some properties, so whether they are stable or unstable, or whether they are there are certain characteristics of the terrain. So the study area that you saw highlighted a moment ago, we will be now overlaid with the slope unit I just mentioned. So here we already made them for you. The data is there. We are loading it as we speak right now. So, and now you can see that we can zoom in on our study area and have our own spatial partition. So how do we subdivide the landscape in this polygonal partition objects or sub-basin available for us? And if you open the properties of them, you can actually showcase or visualize in space what I was mentioning before. So the presence and absence of landslides will be shown in a second. So we are classifying them according to two available values, and you will see that whether a slope hosted a landslide, it will be given a pinkish color, and whether it was stable, so it did not host a landslide, it would have a blue color. And here is a zoom in for you to appreciate the details that we just mentioned. As for what comes, we are trying to predict presence and absences according to some characteristics. And here we will be showing, for example, the spatial distribution of the mean steepness across the entire half basin in your map. So here again, we are plotting the mean steepness with a simple color bar. And you will see that the eastward part of the study area will be steeper, so a darker red color, whereas your westward part of the study area will be much lighter in color, so there is a lot of whitish in there, which expresses essentially the fact that the landscape is a little bit flatter, so a bit of a gentle surface. And here you will have all the predictors that typically we want to use. The y at the end expresses presence and absences. So presence is a 1, absences will be at 0, and all the other properties. For example, for certain properties like the land cover, which is a categorical in itself, we calculated the percentage of this categorical property across the half subbasin, so the slope unit, and the same will be done for other characteristics like lithology, for instance, we will see here expressed, or for other continuous characteristics like the NDVI or the slope, the relief, and whatnot. So once we are in this specific moment, we can think, okay, but we will be using logistic regression. So essentially in a generalized linear model framework. And in this case, we simply use the plugin, selecting the data, selecting the predictors of the covariate that you want the model to use to explain the spatial distribution of landslide presence and absences per slope unit, which we are doing right here, just a subset for matter of simplicity. And here what we are doing, we are selecting the distribution again of 0 and 1, so the column y, so our target variable. And here you will see that you can select certain values for this specific field. We will select in this case 1 if we want the model to use 100% of the data. So we will be fitting for the data for the whole region. We will use greater values if we want to use some cross-validations. We pick a folder and we name the file that we would like to generate with this fitting procedure. we select a folder where to store the data, which we already named for you to store the fit. We select the folder and we let the model run. So the model will take some time. So I will take this occasion to remind we will be using the Y, so presence and absence, and regress it according to this list. And then here we selected 1. The value 1 will mean 100% of the slope unit information will be used to generate our own binary classifier. Okay, so the binary classifier, again, it will be a generalized linear model that uses a binomial family, so a probability distribution typical of basically an exponential family of Bernoulli. And what we'll be estimating is that the relationship between lens-like presence and absences per slope unit will be linear. So we are not allowing, in this particular case, to have any non-linear relationship available in there because of the linear assumption that we chose. We could have implemented, and we are working with Giacomo to add a GAM framework, so a generalized additive model that allow us actually to make more flexible choices in the way that the relationships of landscape characteristic of our covariate are linked to the target variable. It should be ready, so we can close it, and you see a new shapefile available. That shapefile contains all the covariate we listed in the previous choice. Sorry for all these messages, but at the end of it, you will have a column SI for susceptibility index, which is nothing but the probability of lens-like occurrence. Okay, so in this case, we can close it, and we can retrieve now the spatial pattern of it by selecting again a graduate color bar that select a continuous spectrum of values, select the SI column, and here we will select just the magma I particularly like it. We invert the color bar and classify it with 7 classes just for visualization purposes. And as you will see, this is your susceptibility map, generated in a couple of clicks in a few seconds, and then the eastward area is higher in susceptibility. The westward one will be a bit lower. This is kind of reflected in the slope stiffness of the study area, but you have a multivariate contribution in there that can make things more complex. So how do we explore the results? We don't just care about susceptibility, we want to interpret. That's why we use a statistical model. So if we go to our notepad, we open an output file that will be generated. You will see that you have, for all the choices you have made, the global intercept and its relative value, as well as for every single covariate, the corresponding regression coefficient associated to it, which means you can extract these values and essentially generate your own predictive function to predict elsewhere, for instance, or to interpret your model outcome. Okay, so in this sense, this is a fundamental requirement of any statistical model, to be able to understand what the model is telling us and if it makes sense from a physical perspective. But from a performance one, we want to know how it worked. And this is a ROC curve, and as you can see, it will be an output of our model storing or showcasing the value of the area under the curve, okay? Which here is quite acceptable. Of course, this is a tool, but what is a ROC curve? So the ROC curve here is showcased a quick example for you to understand. So on our bar plot, we have absences with the 0. Of course, they are always in any landscape more than the presences in red. And what happens is that when your output of the model will be a continuous spectrum of probability values. So how do we measure the performances? In one side is discrete and the other one is continuous. So what you can do is to cut the probability spectrum into parts and see if what was, let's say, absence will be confirmed as absence, and what's presence is presence again. And this is done here with a confusion matrix. So we will take an example, a theoretical example, for 100,000 grid cells or slope unit, and we will see that the absences that have been estimated can be confirmed as absence in the observation, and the same thing is now done for presences. But So this diagonal that you will see here is the diagonal of the performance that really explains how good the model is, and the other diagonal showcases false prediction. So in this case, presences that have been observed were confirmed as absences, and vice versa. So in green here we show the diagonal that I meant before, that the model performed well in classifying, and the other diagonal false negative, so something that was predicted falsely as an absence condition, and false positive. So these are the four basic metrics in a confusion matrix from which we can obtain some fundamental parameters. There are many to assess binary classification performance. Here we will take the false positive rate and the true positive rate, which you can calculate easily with these equations. And what you do, you can reiterate this slicing of the probability, matching what was blue on one side to what was red on the other side, and then reiterate the computation of the confusion matrix as many times as you need. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and a million times if you need. And what you do, you can then retrieve the values of the true positive rate and false positive rate for any threshold of probability threshold that you chose, and replot it in a two-dimensional space characterized by, again, true positive rate and false positive rate, and reconstruct a curve with each value there is the probability threshold we chose. What happens is that from this curve, you can calculate the integral of it and calculate the area under it, or area under the curve, which is the value that I mentioned before, that it's closer to 1 when it is performing quite well, and it becomes closer to 0.5 or to a bisector, which is what I'm highlighting in the video, when it is, let's say, performing like a coin flipping through the air. So this is essentially the example that I wanted to briefly showcase to explain raw curve and performances in one of the metrics that we implemented in our plugin. So going back to our map, we will now showcase other characteristics of our model. So in this moment we did a fitting procedure, but we can also automatically cross-validate. So we select again the data, we select again the same covariate set. So here I am picking them. We confirm the selection. We will select the vector of presences and absences. And here we select how many fold do we want to run. So here it will be a 10-fold cross-validation. So we will calibrate on 90% of the data and validate on 10%. For instance, if we select a 10-fold, or any other proportion, will essentially, if we select 20, it will do the same operation on 5% of the data for validation and 95 for calibration. And the model, what it does, it will again automatically randomly divide the data set, the 100% of the data set, into a small subset, each one mutually exclusive. So what happens is that the model will calibrate on the large portion, let's say 90% for a 10-fold, 95% for a 20-fold, for instance, which is completely randomized in the selection. And then it will regress presence and absences for the same covariate, following the choice that you picked for your cross-validation routine, how many times you iterated the sampling strategy. That's the output, as you can see. So what will we be doing here will be two operations. Plot it against in space. So what the procedure has done, that at every bootstrap replicate, it stored the predictive value, so the probability of Lenzler occurrence, for every subset, whose union is giving us the total study area again. So if we plot it, now we will be selecting again a magma color bar just for comparison with the previous one. Inverting it, selecting 7 classes once more. And the variations, of course, will be very limited with respect to the previous map, because using 90% of the data for a linear model that has little variability in space, most likely will generate the same data, so the same spatial pattern. So differences are really very localized. Overall, the pattern we retrieve is the same. You can control much more how the predictive value change if you use other techniques for cross-validation, for example, spatial cross-validation. Here you have again the susceptibility index once more. And what we want to do is again interpret the output. So we can go again on our folder where we stored the outcome of the regression coefficient, this time replicated a number of times equal to the replicate you chose. So the first column will store the same intercept and predictors you picked, and the intercept, as you can see, has several values associated to it, and the model is actually quite stable. As you can see, the variability is small. Same thing goes for the other covariates, so the relief here, very relatively small variability, sign is the same, magnitude slightly changes of it, and the same you can check for the others. But what about, so aside from interpretability, you can have the plotting tool for performance metric. This time you have a 10-fold cross-validation, therefore you will have 10 ROC curves. And in this case, the best performing one has a 0.8 of AUC, and the worst one has a 0.64. So this is just to showcase how this SZ plugin has everything that the standard procedures for susceptibility model typically require. You will check the last tool of this plugin, which will be controlling the random proportion, the random selection with specific percentages. So what you can do for single fold, so you only iterate the model once, you again select covariate, select the Y, so the presence and absences, and in this case you select exactly the proportion. So you want to select 20%, the model will do one iteration where you will do 80% for calibration, 80% of the data, and 20% of the data for validation as an hidden data set that the model was blind towards. So again, we save the output in one folder for this essentially calibration validation procedure, which we'll call here a file training and test essentially. We select the folder where to store it, and we run our SZ plugin once more. Again, the same structure. Our Y is regressed against the series of covariate we picked, and this time you will have this value, 20% of the data used for validation. So the complementary case will be used to train, and the actual value in percentage will be the location where we will estimate the predictive capacity of our model. And as you saw, there will be two outputs in this case. One for calibration, so how the model will perform in explaining the 80% in itself, and how much the model will be performing in explaining the remaining 20%. So let's give us a second for completing the regression procedure. Here we finish the procedure, and now we can open. As you can see, the output will be divided into two. So one is for train and one is for validation. So we will turn off the bottom layer, and you will see now that the area is divided into two shapefiles. The one for validation will be much fewer, and specifically 20%, and as you can see, randomly distributed in space. And as you can see, the same information stored before will be stored here. So you will have a susceptibility index, or the probability of occurrences, for both data. So both for the calibration, the 80%, as well as the validation, the remaining 20%. So this is essentially what we would like to showcase for today. The same thing that we had before will be plotted in terms of performance metrics here, dividing two ROC curves, one for the 80% and one for the 20%. And with this, essentially, I would like to thank you, and we'll see you again for the next video.